Hi, I am Saptarshi Mandal, a postdoctoral researcher in the IBS Center. Today I will present adsorbed water structure on acrylate-based biocompatible polymer surfaces. Now let's discuss why is this study important. The biocompatible polymers are very promising materials that are used commercially as an anti-biofouling coating material for artificial organs, contact lenses, catheters, surgical instruments, and various other biomedical applications. Biocompatible polymers are those which do not interact with the blood proteins or platelets in a physiological condition, unlike non-biocompatible materials which do interact severely. Numerous research was conducted to understand various factors that affect the degree of biocompatibility of these polymers. It was found that there are interesting correlations between the nature of water present on these surfaces and their corresponding biocompatible behavior. Based on the mobility and freezing point temperature, non-freezing water, intermediate water, and free water were identified. Even it was observed that water can be more concentrated on the biocompatible surfaces. However, the dynamical aspect of the water-hydrogen bonded network around these biocompatible materials, about how they impact their behavior, was grossly overlooked in the previous studies. Therefore, in this study, we investigate the structure and dynamics of adsorbed water in excellent biocompatible material poly 2-methoxyethyl acrylate or PMA, which we compare with that in poorly biocompatible poly 2-phenoxyethyl acrylate or PPA. PMA is about 3 to 4 times more biocompatible than PPA polymer when blood protein adsorption or platelet adhesion are compared. These polymers have two different functional groups in their side chain. Therefore, understanding how water structure and dynamics change could help us correlate their biocompatible behavior. First, we measured the FTIR spectra of the OD stretch mode of water and carbonyl stretch mode of the polymer side chain. OD stretch mode in PMA is blue shifted, whereas it is red shifted in PPA polymer compared to that in pure water. However, the carbonyl stretch mode is always red shifted. This observation clearly indicates that the water hydrogen bonded network could be very different in these two polymers. Deconvolution of the carbonyl stretch band using two Gaussian functions suggests a significant increase of the FWHM of the peak corresponding to the hydrogen bonded carbonyl moiety compared to that in PPA polymer. After that, we calculated 2D correlation spectra in the range of 1400 to 1800 centimeter inverse from the kinetic FTIR data measured over a day for both the polymers. 2D correlation spectra can reveal the interaction between different normal modes of vibration. Here it can be viewed that cross-peak appears between water OD stretch and carbonyl stretch mode, particularly for PMA, but this cross-peak is very weak in the case of PPA polymer, which can be seen from figure C. These 2D correlation spectra indicate a strong in-phase correlation between water and carbonyl stretch mode in PMA polymer. Then we performed ultrafast pump-probe spectroscopy of the isotopically diluted water adsorbed in these polymeric surfaces. This is the schematics of our pump probe instruments, and this is the raw IR pump probe data of the OD stretch mode in respectively water, PMA and PPA polymer. It can be observed that the IR pump probe spectra are substantially contaminated by the pump induced scattering fields, and this is quite a common challenge when measuring the pump probe spectra from the complex heterogeneous surface. Hence, denoising of the pump probe data is necessary for quantitative analysis. To denoise the IR pump probe spectra of the OD stretch mode, we used the discrete wavelet transform algorithm, which is very similar to the first Fourier transform method but has significant advantages over FFT in describing abrupt changes of the signal in frequency and time domain. In this method, an analyzing function is used, which is a wavelet. This wavelet is a function of scaling and shifting parameters that are required to change the size and shape of the wavelet at a particular data point. The noisy signal is deconvoluted in various component spectra, and then those components which are very close to the oscillatory response of the pump, as can be viewed in the second figure, can be removed to get the denoised spectra. This process is repeated for the OD stretch mode, both in frequency and time domain. Now, here we present both noisy and denoised IRPP spectra of the OD stretch mode after DWT correction for both the polymers. And this bottom figure suggests that DWT works perfectly in suppressing most of the oscillatory noise. Now, if we compare the denoised IRPP signal of the OD stretch, we can clearly observe that the vibrational dynamics of OD in PPA are significantly longer than that in PMEA polymer. However, to make sure that this DWT algorithm works for any system, we apply the same method to denoise the cyanide stretch mode of phenyl cyanide in ethanol. Here, scattered pump probe spectra are generated by intentionally scratching the calcium fluoride window. This figure shows the denoising process at different delay times. By applying this DWT method in both frequency and time domain, we get the denoised IRPP spectra of the cyanide stretch, which can be visualized from figure C. Therefore, the DWT method is very reliable and can be applied to various systems. We then performed the global fitting analysis of the OD stretch IR pump probe spectra to get the eigenspectra which represent different chemical species. For both PMEA and PPA polymer, we get two eigenspectra which are respectively red shifted and blue shifted compared to pure water. The vibrational dynamics of the blue shifted water is fast compared to the red shifted water, and red shifted water dynamics is slow. We assign the blue shifted water to the bulk like water as this blue shifted water has a similar lifetime. We also performed molecular dynamic simulation and quantum chemical calculations which show that these blue shifted water appears due to their weak to moderately strong non-covalent interactions with the hydrophobic methoxy and phenoxy terminal group, respectively for PMEA and PPA polymer. However, the red-shifted water represents the hydrogen bonded water to the carbonyl moiety of the polymer side chain. Interestingly, the vibrational relaxation dynamics of this red-shifted water in PPA is more than 2.5 times slower compared to that in PMA. In this figure, we compare the vibrational dynamics of water at the blue and the red edge of the IRPP spectra. It can be observed that as we go from 2585 centimeter inverse to 2485 centimeter inverse, that is from the blue to the red edge, vibrational dynamics of water becomes significantly slow in both these polymers. However, in PPA, this has become much slower. Further, we also measured mid-IR photothermal microscopy of the carbonyl stretch and water bending mode. Photothermal image of carbonyl mode was extracted by removing the water contribution as exciting at the carbonyl region excites both CO stretch and OH bend. From this figure, it can be viewed that PMEA shows more photothermal signal than PPA, which suggests that there are more carbonyl moieties that are hydrogen bonded to water. We also see a stark difference in surface morphology in these two polymers. Finally, we can conclude that the red-shifted water corresponds to the water hydrogen bonded to the carbonyl moiety of the polymer, whereas blue-shifted water is organized around the hydrophobic terminal groups of the polymer side chains. Molecular dynamics simulation, in combination with the quantum chemical calculations, suggests that these blue-shifted water molecules substantially modulate the vibrational dynamics of the red-shifted water, which are hydrogen bonded to the carbonyl group. On the dynamics, we can infer that a substantial population of the red-shifted water in PPA preferentially relaxes through the inefficient CO-DO hydrogen bonding interaction, and that is why the vibrational dynamics is exceptionally slow for this water. However, redshifted water relaxes through both efficient Fermi resonance pathway as well as CO-DO hydrogen bonding interaction in the case of PMA, which explains relatively faster vibrational dynamics of this redshifted water in PMA than in PPA. Finally, to better understand the mechanism and this work as a whole, please have a look at this publication. Thank you for listening.